Right, we need to get started talking about motion, and we're going to dive into that slowly. To begin with, we're just going to discuss the basics of motion. We're just going to define some terms at first. We can talk about motion in a lot of ways. The study of motion includes kinematics. That's just the description of motion. That's kind of what we're getting into now. We can also talk about dynamics, which are changes in motion. We're not going to get there for a little while. For right now, we're just going to talk about one-dimensional motion, which is, we say 1D, that's just motion in a straight line. We might move one direction, and then we could go back the other direction, but that's motion all in a straight line. We're not changing directions. We're not doing any of that stuff. Okay, this is just motion in a straight line. So some definitions you need to know at first. Again, this is following along in your notes. Position is the first thing you have, and that's the separation between an object and its reference point. This is somewhat of an arbitrary term. In other words, it's just how far an object is from the origin. It's pretty simple. So if an object starts at this point and it moves over to here, position describes the distance from here to here. Okay, and we've already used the term distance to describe this, but distance is the next term that we need to know. With distance, it doesn't really need a reference point. All you simply do is measure the distance, which you already know what that is, between two objects by measuring their separation. Pretty simple, right? A closely related term, however, is displacement. Displacement is the change in position. In other words, delta D, we'll talk about that in a second. Delta D is what we use to denote change in position or displacement. Change in position of an object. In other words, and this is a very important definition to remember, it's the straight line distance between two objects and their direction from one to another. Or it could be the straight line distance from the beginning of an object's path to the end of an object's path. So we might start here and end here. Okay? Straight line distance between two objects, or the straight line distance from the beginning of a trip to the end of a trip. So as I said, displacement, change in position. Typically it's denoted by delta D. And delta D, to calculate that, you'll see two formulas specifically. D1 and D2 stand for, D1 stands for the initial position. D2 stands for the final position. So we go final position minus initial position to calculate the displacement. And also, most of the time, and this is the one that I like to use because it's more intuitive, F stands for final, I stands for initial, DF minus DI, final position minus initial position. This is a very important point. You need to put a star by this. In this class, we're going to arbitrarily decide, well, not really arbitrarily, but to go to the right or to go up is a positive direction. And then left and down will be negative. This is in reference to the good old coordinate axes that you're used to in math. You know that positive direction is to the right and up, and negative directions are to the left and down. Okay, so we're going to use the same convention here in this class. It'll help us out. That'll happen in about 95% of the things that we calculate in here. We've got to talk about direction, and usually we indicate direction with negatives and positives. Okay, negatives and positives in this class are indicators of direction of movement, or direction of a vector, a force, something that's moving in a certain direction. We can also say up, down, left, and right, but a lot of times we just say negative and positive. This is not as important, but change in time is also written the same as displacement. We say delta T instead of delta D. It's denoted as delta T. And you'll see that just like displacement, T2 minus T1, or TF minus TI, final minus initial. Don't worry about this one. TF minus TI. Okay, so as a simple example, we can picture this lizard that is moving to the right, indicated by this arrow, and I want to know what distance does the lizard travel and what is the lizard's displacement. Okay, so distance, remember, we're not concerned about direction. Okay, so we can look at this lizard and it tells us that the starting point is here. Looks like approximately 25 centimeters is what we'll call it, and the final over here is 85 centimeters. And if you remember that distance is calculated by taking the final position minus the initial position. So 85 minus 25 gives us a distance of 60 centimeters. And then displacement is almost the same as distance. The only thing we add in there with displacement is we're concerned about the direction. So that we would say that the lizard's displacement is 60 centimeters to the right, okay, not to the left. The lizard is moving to the right. Okay, here is the final position. If the final position was here and the initial position was here, we would say the displacement would be to the left, but it would still be 60 centimeters. So I want you to look at these three for a minute. And see what you come up with. Determine the displacement of each. Okay, hopefully you've thought about it. Let's go with this one here. Get my pen back over here. Final position, initial position. This one, 80 minus 10. So it would be moving 70 centimeters. That would be the distance. And the displacement is simply adding in the direction, 70 centimeters to the right. All right. This one here looks like we started at 15 centimeters and we moved to 0. 0 minus 15 would be a negative 15. So we would say the distance would be 15 centimeters, but the displacement is 15 centimeters to the left, or we might just say negative 15. Remember, negative indicates a leftward movement, a negative direction. 16 centimeters is also what we're going to get here. I'm sorry, we had 15. 16 centimeters is what we'll get here because the final position is 6 and the initial position is negative 10. 6 minus a negative 10 is a positive 16. So that's why we would say the displacement is 16 centimeters to the right. And here we have final position negative 20. Initial position negative 10. So final minus initial, negative 20 minus a negative 10 gives us negative 10 centimeters. So we would say, again, distance is 10 centimeters, not concerned about direction with distance. Displacement, we would say 10 centimeters to the left, or it would be negative 10. All right, and this brings up the concept of scalars and vectors. Scalars and vectors. It sounds like a complicated term, but it's actually pretty simple. And this is not in your notes. I want you to put this in your notes to the right of that displacement and time section. It's a very, very simple section. All you need to do is write down these two statements. Scalar has only magnitude or size. In other words, that's a number, okay? And a scalar measurement, an example of a scalar measurement is distance, for example. I'm trying to write with my mouse. A vector, on the other hand, has both magnitude and direction. So vector, all you do is you add in the direction, okay? With distance, we're only concerned about how far did we go. With a displacement, we're concerned about how far did we go and in what direction. Distance would be the scalar quantity and displacement would be the vector quantity. Scalar and vector. So again, scalar is only a magnitude, that's just a number. Just a number. For instance, for the scalar, you can think about a scale. You use a scale to measure your weight. And if you tell somebody your weight, if they say, how much do you weigh? You wouldn't say 150 down, because it doesn't matter down or up. Now, when we actually talk about later, weight is actually a force and it is directed down, but that's different. Right now, all you know is that weight is just a number. You say 150. Direction is not a part of that. That's an example of a scalar quantity. Whereas a vector would be both magnitude and direction. So if you say, how far is it to your house? Somebody might say, I live 15 miles north of here. That's a magnitude, a number, and it has a direction, 15 miles to the north. Examples of scalar quantities are these: distance, speed, mass, time, density, work, energy. A lot of these things we're going to get to later on. Vector quantities, these are counterparts. The counterpart of distance is displacement. Displacement is distance with a direction added in. Same thing with speed and velocity. Velocity is the vector counterpart of speed. These down here are a little bit different. Acceleration, force, and momentum, all of those are going to be vector quantities as well. Question for you. Think about this for just a minute. I'll pause the video. Is distance and displacement always going to be the same number? It has been so far in the examples we've done. Will distance and displacement always be the same number?